My name is Larry Harris. I'm a technical coordinator here at the RTP. I teach training classes and PLCs. PLC is a programmable logic controller. A programmable logic controller is basically a computer that's about the size of a juice box. This unit here is a PLC unit with I/O and communications modules. An I/O module is an input-output module. It gives us an ability to actually feed the information into the PLC. All the inputs for a PLC relate to a computer. You get all of your inputs from a keyboard and from a mouse. With a PLC, we're going to do it with switches, buttons, and other input devices. We also teach classes in the logic that's actually used to control it. The logic is what they refer to as ladder logic. It's a symbolic programming language where we use symbols instead of using a textual-based programming language. The first rung of logic we have here is very simple. We have a contact, which represents a switch. When the switch is not on, it will be open, so there you see no green or power flow through that switch. The next contact we have here is a normally closed contact. In this case, we get power flow when the switch is not on. So we can look at a switch and determine whether we want to use it in its state of being on or in a state of it being off, open, or closed. By arranging these contacts in a certain order, we can manipulate an output. The way it is currently arranged here, if I press the button on the screen, it completes the rung of logic and the cylinder extends. If I remove the input, which basically is turning off this first input, the cylinder will retract. What we generally do in the basic class is we start on Monday morning and we talk about the inputs and the outputs and the different kinds of field devices that we can have. And then we start getting into the actual logic programming itself. With the logic programming, we start simple, open contact, closed contact, and an output. So the first thing they do is they learn how to manipulate an output with a one-to-one relationship based on an input. And then we build on that. We go a little further into the process and we're saying, what do we do if we want something to occur, but I'm too lazy to stand here and hold this button? So we increase the scenario a little bit and we make it a little more difficult. What we've done in this case is we add a branching circuit here to where our output is actually one of our inputs. And by putting that branching circuit in, now I can press the button and it will come on and it will stay on until this limit switch is actually activated. So it opens the circuit, cutting off power to the cylinder. Once it turns off power to the cylinder, then the cylinder will fully retract. We start at that point, we move through our HMI programs. This is basically a cylinder that we're going to use to increment a conveyor a set distance every time the cylinder is actuated. It's basically the same thing. I've got inputs, outputs, the same basic logic structure. So that gives you a little idea of the next step in the process. Then we go a little bit further and now we get into timers and counters. So what we do in our next program is we build on what we've already got. In this one, we're actually using two timers to determine how long we leave an operation in place, how long we leave something on. In this case, we have a little gate here that we have to open, and we have to leave it open for 1 second in order to allow material to pass. After 1 second, we close that gate and we move to the next step in the process. Once we've got that in place, we let them go through the process. It'll go down, it'll delay for 1 second, it'll come back up, and then go back through the sequence. So then we go a little bit further and we incorporate counters. In this case with the counter, we have a small value placed in. We're counting pulses off of a pump to let us know how much liquid we have actually pumped into a container, in this case a bottle. So we're using a counter to control that. When the count gets to a certain point, we turn off the pump itself, knowing that we have the right amount of liquid in the bottle. Still relatively simple. The little robot picks a cap, goes down. We're using a torque sensor, so we're using an analog input to determine that we have the correct pressure on the cap. Once the torque level is achieved, it turns off the twist routine, turns off the place routine, so the robot goes back to the home position, clears out any memory bits that we've used, and it's ready for the next cycle. Once everybody has done all of that, we tell them that the next logical step in the process is taking each one of these individual machines that we've created and make them work in an automated function. And we try to tell everybody, and we try to get them to understand that the majority of the things that happen in this world happen in a sequence of events. So what we try to do is we try to take a complicated piece of equipment and break it down into individual portions and then program each individual portion and then daisy chain them together. So this is a bottling line that they actually end up programming. So if I start the process, it indexes the conveyor. It'll place a bottle on the conveyor. On the next index, it'll place a bottle. It'll fill the previous bottle. It'll index again. And now we have an ongoing operation. If you start people out with this screen on Monday morning, they don't come back on Tuesday morning because they see it as being a monster. It's huge. There's a lot of stuff going on. So what we do is we break it down into the individual pieces. After we do that, we have people program a simple calculator. In this case, we have two numbers set up to where they can use a keypad to put values in. They press the math instruction that they want, press equal, and it should give them the correct result. They actually have to program all this in the background as far as what the input instructions are, first instruction, second instruction, and then the actual application. Am I going to multiply it, divide it, add, or subtract it? Once they've got that, we move a little bit further and we play with a little garage. We use an increment instruction, a decrement instruction. We actually reset some numerical values. So all of this is based on a word level. So this is pretty simple. Everybody knows how a parking garage works. We set limits on this program. They're only allowed to put 40 in the lot. That's all it'll physically hold. And they're only allowed to remove vehicles to the point that they get down to zero. If we don't have any cars in the lot, we can't have any leaving. They go through and they write their program. They have to put their limits in to be sure that it will not go negative. When the value in the lot here is at zero, the car leaves button is held in a non-functional state, so it will not function to subtract one from the number. By the same token, when the lot gets full, if the lot's full, we do not allow the car enters button to actually function. After that, we have a little drill press. We count how many holes are drilled. In this scenario, what we want to do is we want to be sure that we don't break any bits. We realize we can drill so many holes, we can resharpen the bits, and we can drill so many more. But if we exceed the number of holes that we can drill with it, we end up breaking the bit, therefore rendering it useless. Loss of profit. So we keep up with the number of holes that is actually drilled. Once you get to the point that if I try to drill 3 holes and my count is at 18, we actually disable that button so we can't go over 20, destroying the bit. We have a simple shift conveyor here. We have good boards. Every time we put a good board on the line, the operator places it on the conveyor. If we put a bad board on the line, the operator puts it in the trash. It's actually a simple increment instruction to keep account of how many good and how many bad. We've modified the program a little bit to include that if we get a total of 3 bad in a row, that it turns off power to the line. Last thing we have is our little infamous washing machine. We use a multiplex instruction in addition to the timers and a couple of counters. And we'll make some pretty lights move, and we fill the liquid level of the tank. It gets 10 seconds to fill the tank. We have a numerical value here from 0 to 100. You fill up the tank in 10 seconds. 10 times 10, that'd work. We agitate the tank for 15 seconds. While we're agitating the tank, all the indicator lights across the top flash. After 15 seconds has passed, we have to drain the tank to get all that dirty water out. We have 10 seconds to drain the tank, and we want the indicator in this case to walk from the left to the right. Once we hit the spin cycle, we do the little Knight Rider thing. We bounce a bit left to right across the indicator lights at the top. As a follow-up to that, we want to be sure that our clothes are clean, so we run an entire separate system or a separate cycle for each of the 4 cycles again. And this is all in the basic class. When we get into the intermediate class, what we do is we look at different methods of programming. Instead of just using ladder logic, we get into structured text, function block programming, and sequential function charts. So it's 3 more methods. Typically what we do is we take all the programs that they've done in their basic class and we rewrite them in a different programming language. After the intermediate class, we have an advanced class. In the advanced class, it's pretty much all networking. So we end up with a total of 16 networks running in the classroom, to where if I flip this switch on this trainer, any piece of equipment in the room can actually get to it through more than 3 different methods. So we have some built-in redundancy. All of our classes are 40-hour classes. And in most cases, it takes all 40 hours.